Okay, so welcome to the third video on this series of how to solve a circuit 5 different ways. We're solving this circuit down here on screen, and what we have found is that we can build the circuit and measure it, and we can also use the approach of using Kirchhoff's laws, the current law and the voltage law. And when we do so, we found that we had 2.5 milliamps going down this resistor, 0.5 milliamps going upwards, and 2 milliamps going up on the left here. And that was just using Kirchhoff's laws to grind out a system of equations, kind of in a brute force way. We're going to use a different approach today, that is the approach of superposition. Now the idea of superposition of linear systems is as follows. If I have an input and it produces a given output, I can double that input and the output will double. Similarly, I can add two separate inputs, and the output I'm going to get is the sum of what I would have gotten if I did those individually. So in this case, we can double our voltages, and the resultant currents are going to double through the resistors, because voltage sources, resistors, and a few other things we study like capacitors and inductors and amplifiers can all be considered linear systems under the right conditions. And this is a very neat way. When you actually think about how this works, or what this actually says, it's quite a cool idea. It says effectively that what each resistor sees is the sum of a 9-volt battery driving current through it one way, and a 6-volt battery, and the current that results is the sum of the individual currents that would have resulted from those batteries individually. So they all act independently of one another. Now we can use that to solve a circuit. So let's try to draw that out. That's saying the superposition principle is saying that this circuit is actually equivalent to the sum of two circuits. It's the sum of this circuit, just moving it down there. It's a sum of one circuit with just a 9-volt battery driving it, plus a second circuit, which is driven just with a 6-volt battery. Now each of these circuits will yield voltage drops and current through each of the resistors, and the end result, the one that I'll get on top here, is just going to be the sum of those two values for each resistor. So let's actually grind that out and see what we get. It leads to a much simpler analysis in this case. So we'll start with the one on the left. This circuit is actually equivalent to a simpler circuit. The two 2K resistors in parallel yield a 1K resistor equivalent, just from the laws of parallel addition. And the current through that circuit is just going to be the voltage divided by the total resistance. Which is 3 milliamps. Okay, that's good. We can kind of back solve now. So we can write this circuit as follows. Note that we had a voltage drop of 3 milliamps times 1K, which is 3 volts here. So each of these 2K resistors has 3 volts across it. 3 volts between these 2 points. And there will be correspondingly 6 volts across the other resistor. But that means that I have 3 volts over 2 kilo ohms, or 1.5 milliamps through each of these circuits, through each of these resistors rather. So our circuit here is a 3-volt drop across these two resistors, a 6-volt drop, the rest of it, across the other 2K resistor here, and we have 1.5 milliamps through each of the 2K resistors, and 2K on the one on the left. Okay. So that's that circuit. That's great. I'll just move this out of the way for a second here. Let's look at the other circuit now. Well, in this case, we have a 6-volt and an equivalent 1 kilo ohm resistor as before, 1K. 6 volts and a 2K here, with a corresponding current going the other way here of what? Of 6 volts over 3 kilo ohms equals 2 milliamps. So there's 2 milliamps going through here. That means there's 2 milliamps going up through that resistor. We have the same analysis applying to these other 2K resistors. So we can see it a number of different ways. 2 milliamps through 1K is 2 volts through there, or they're equal values, or they all have to add up. Either way you look at it, we're going to get 1 milliamp going through, 1 milliamp going through these 2 resistors. And the voltage drop, for example, across here, of the central 2K is now going to be 2 kilo ohms times 1 milliamp, or 2 volts. So you have 2 volts across the central resistor, and a milliamp going downwards through it. And we're almost done. Now we just add up these 2 circuits. So let's go back up to the top here and just add up what we had. We have 1.5 milliamps going down, and from the other circuit we had 1 milliamp. So the total is going to equal 2.5 milliamps. Okay, let's look at the other parts. So we had 2 milliamps going up from the circuit on the left, and 1.5 milliamps going down, or sorry, we had 2 milliamps going down from the circuit on the right, and 1.5 milliamps going from the circuit on the left. If we add these 2 up, we're going to get a total of 0.5 milliamps. And what do we have on the final one? We had, well, let's look, we had 1 milliamp going down and 3 milliamps going up. I'll keep the same color scheme. And exploiting superposition of linear systems, we just add them up, and we get a net 2 milliamps upwards. So this is quite a cool picture of what's going on here. Each battery is driving its own current through the resistor, and we see the net effect of both of them, and we get the same answers we did before. Just to finalize it, our voltage drop here from the across these resistors, we had 2 volts from the circuit on the right and 3 volts from the circuit on the left, for a total of 5 volts across this resistor, which is exactly what we found with the measurement technique and the Kirchhoff approach. So in the next video, we're going to apply yet another technique, the Thevenin equivalent approach, before finally just simulating it on a computer. All right.